Hello. Today we'll be presenting our machine learning final project for CS4641. Our group, consisting of myself, Kyle, Sabine, and Azia, utilized various machine learning techniques in order to detect the presence of COVID-19 through CT lung scans. Our goal is to create a model that will learn from the lung CT scan dataset to determine whether or not new patients are at risk for pneumonia as a result of being COVID-19 positive. With the new knowledge surrounding the virus, it becomes much more crucial that patients seek special attention if the virus has infected the lungs. With this model, doctors only need to upload the CT scan from the patient, and the model will give vital, potentially life saving information on the next step of treatment. We use the lung CT scans provided on Kaggle to determine whether a patient has COVID 19. We then applied a set of unsupervised and supervised learning techniques on this dataset to both gain an insight and predict whether or not a patient has COVID.
In terms of unsupervised learning, we decided to use 4 different techniques to gain insight from our dataset. We also applied data cleaning methods in preparation for supervised learning. For data cleaning, we grayscaled the images, converted all our image file types to one consistent file type, and converted all the images to 224 by 224 for supervised learning purposes. One of the unsupervised learning techniques used was CAM, also known as class activation maps. It highlighted the parts of the images that the neural network focuses on in supervised learning so we can better understand how our neural network will work. It gives us an idea of what part of the data has to be focused on by building a heat map. The VGG16 architecture output seems to focus more on the heart area than the rest of the lung scan, but the ResNet architecture output highlights the ground glass opacities, which is indicative of COVID-19. In conclusion, the CAM model tells us that ground glass opacity is a possible important feature. Another unsupervised technique used was dbScan. Using dbScan in segmentation highlights the lung cavities the most. For the most part, dbScan clusters by lung boundaries. COVID-positive images noticeably cluster centers of the lung in much smaller proportions compared to COVID-negative images. Even though dbScan segments images decently, the widely different epsilon parameter needed for each images makes it unideal for any further use other than visual insights. We also ran the GMM algorithm in order to view the various groupings within the CT scans. The most noteworthy outcome of GMM was the fact that it picks up on ground glass opacities, which is important in diagnosing COVID. However, GMM could not run on multiple images at once, so it was unable to group together similar images. Instead, we focused on drawing conclusions from one image at a time. We additionally utilized PCA. PCA was able to successfully reduce the dimensionality of data. 99% of variance was able to be recovered while dropping a majority of the components. However, we did not apply this outside of the unsupervised learning methods. It did highlight some ground glass opacities, but we believe that the introduced reduction in sharpness would hinder our ability to create an accurate supervised learning model.
For the supervised portion, we decided to use convolutional neural networks in order to predict whether or not someone has COVID. When it came to data cleaning, we had it prepped to scale from 0 to 255, did a random shear of zero point 0.2, and a random zoom of zero point 0.2 in order to avoid some degree of overfitting when it came to training. We used the image data generator class to achieve this. In terms of splitting our data between training, validating, and testing, we had 70% for training, 20% for validation, and 10% for testing. In addition, we programmed 15 epochs, but the model itself stops training if there is no major improvement in loss between epochs. This also helped prevent overfitting on the training set. The current CNN model structure is a 2D convolution with max pooling, then another convolution with max pooling, and then a third and final convolution with max pooling. Then the model flattens the image before it's fed into the fully connected layers with dropout. On the fully connected layers portion of the model, we have 2 layers of neural networks with 2 different activation functions. The first layer uses the ReLU activation, and the second layer uses the sigmoid activation. When the model is compiled, we use the Atom optimizer as well as the binary cross entropy loss function. At this point, after we trained and tested the set, we found that we had an 84.36% accuracy with a 0.0471 loss. This is a great start. We want to be as confident as possible in our COVID diagnosis. We can further improve accuracy by applying different data augmentation techniques to reduce overfitting. After our touchpoint 3 feedback, we attempted to generalize more by applying different data augmentation methods such as increasing the shear in the zoom. This was largely successful, increasing our test set accuracy to 90.5%. We also attempted to use the ResNet 50 architecture. Unfortunately, it did not work as we anticipated. Training took a long time, and the model was quite inaccurate as well. Afterwards, we added a random zoom, and that pushed the model's accuracy to 93.68%. Overall, 93.68% is very good for a model that's training on a dataset of lung CT scans. Knowing that we have a relatively high accuracy on this set, medical professionals will significantly benefit from being able to check whether or not a patient has COVID with high confidence.
The significance of this relates back to the ease with which doctors will be able to rapidly confirm patients' conditions, and subsequently be able to use this information for deciding which route to take with treatment. Looking at both the demonstrated unsupervised and supervised techniques, they will be especially significant for at-risk patients if the CT scan can reveal the results faster than a saliva or a nose swab test. This concludes our final project presentation.